Most people think black holes are just giant dark objects that suck everything around them in. But what has always struck me as strange isn't the black holes themselves. It's what happens to time when you get too close to one. Imagine an astronaut falling toward a black hole with a mass millions of times that of the sun. If you observe from very far away, you'll see that person slow down, slower and slower, then almost come to a stop right at the event horizon. The light from the astronaut's suit gradually turns red as gravity stretches each wavelength, just as Einstein predicted in 1915. From your perspective, that person never actually enters the black hole. But from the astronaut's own point of view, nothing special is happening. His clock is still ticking normally. His heart is still beating normally. He just keeps falling into the darkness. According to Einstein's mathematics, both of these things are true at the same time. And that's when you start to realize that the strangest things in the universe appear when we take the equations too seriously. And the funny thing is, this whole story actually began with a man who lived more than 200 years before Einstein. In 1687, Isaac Newton published his law of gravity in the book Principia Mathematica. And honestly, it worked so beautifully, it was almost scary. With just a few equations, Newton could explain the orbits of the planets, the motion of comets, the tides, and even accurately predict the positions of celestial bodies decades into the future. For more than 2 centuries, Newton's gravity worked almost perfectly. But here's the most interesting part. Newton himself was never comfortable with his own theory. He couldn't understand how 2 objects could attract each other across empty space without anything connecting them. That idea bothered him. Then, at the beginning of the 20th century, Albert Einstein began looking at gravity in a completely different way. He suggested that gravity might not be an invisible force pulling things together. Maybe what we call gravity is actually the shape of space and time itself. According to Einstein, the sun doesn't pull the earth around it. The sun curves the fabric of space-time around itself, and the earth is simply moving along that curved shape, like a marble rolling on a slanted surface. In 1915, Einstein published the general theory of relativity, and for the first time gravity was described as geometry rather than a force. It sounds abstract, but his equations immediately began producing extremely strange predictions. One of them was that light itself is bent by gravity. In 1919, during a total solar eclipse, Arthur Eddington measured the light from stars behind the sun being deflected exactly as Einstein had predicted. Just a few days later, Einstein became the most famous scientist in the world. But things got much stranger than that. According to relativity, gravity doesn't just bend space. It also slows down time. A clock placed near a very heavy object will run slower than one farther away. And this isn't philosophy or imagination. Since the 1970s, atomic clocks have measured this effect with extreme precision. What always strikes me as both beautiful and terrifying about physics is that mathematics is often right even when all human instincts say it can't possibly be. And when physicists continued to dig deeper into Einstein's equations, what began to emerge from them were black holes. What I always find interesting is that the first person who truly saw this wasn't Einstein. It was Karl Schwarzschild, a German physicist serving on the front lines during World War I in 1916. Try to imagine that for a moment. Europe was plunged in war, artillery exploding everywhere, millions dying in the trenches, and somewhere in the middle of that chaos, a man was sitting and solving the most difficult equations ever written about gravity. Just a few months after Einstein published the general theory of relativity, Schwarzschild found the first exact solution to Einstein's field equations. And this is where things started to get truly strange. Schwarzschild wasn't trying to create black holes. He just wanted to describe the space-time around a non-rotating spherical object like the sun. But as he followed the mathematics to its conclusion, the equations began to show something terrifying. If enough mass was compressed into a small enough region, the structure of space-time would collapse in on itself. Schwarzschild discovered that there exists a special distance around any massive object. If you go inside that boundary, the speed needed to escape would be greater than the speed of light, about 300,000 kilometers per second. Today we call that distance the Schwarzschild radius, and this is the part where human intuition begins to fail completely. If you took the entire mass of the sun and compressed it down into a sphere with a radius of about 3 kilometers, smaller than a city, the sun would turn into a black hole. Not because it suddenly became greedy or sucked harder like movies often show, but because the space-time around it was curved so severely that every possible path led inward. Even light could not escape. And if light can't escape, you can't see anything from inside that region. That's why we call them black holes. But in the early 20th century, almost no one believed nature would actually allow this to happen. Most physicists saw it as a mathematical oddity rather than a real object in the universe. Even Einstein didn't believe a star could collapse infinitely like that. This has happened quite often in the history of physics. Mathematics sometimes leads us to places that even the people who created the equations don't want to go. And what I always find both beautiful and terrifying is that black holes were first born on paper rather than through telescopes. No one saw them at first. No one photographed them. They appeared because the equations said they had to exist if Einstein was right. This was the first time physics truly began predicting the existence of regions in the universe where all ordinary human intuition completely breaks down. And trust me, things got much stranger when stars started to die. Most people look up at night sky and think stars are just giant balls of fire burning somewhere in space. But a star is actually a billion-year-long battle between two forces trying to destroy each other. One is gravity, which always wants to crush all matter into a smaller point. The other is nuclear fusion in the star's core, constantly producing enormous pressure to resist that collapse. In the case of our sun, every second about 600 million tons of hydrogen are fused into helium in a core that's about 15 million degrees Celsius. About 4 million tons of matter are converted directly into energy every second, according to Einstein's famous equation. That's what's lighting up the entire solar system right now. It's also why Earth hasn't frozen into a dead rock. For nearly 5 billion years, gravity has tried to crush the sun, while nuclear fusion has tried to push it outward. The two forces have maintained an almost perfect balance. But here's what always makes me find the universe a bit scary. Gravity never gets tired. It doesn't sleep. It doesn't stop. It just patiently waits for the star to run out of fuel. And at some point, the core no longer has enough hydrogen to keep generating pressure against gravity. When that happens, gravity starts to win. The entire star begins to collapse under its own weight. The core temperature rises. Pressure increases dramatically. The outer layers become chaotic. For smaller stars like our sun, the final nuclear reactions will eventually push the outer layers out into space, leaving a hot, dense core behind. But if physics only had classical gravity, every star would probably have collapsed completely long ago. This is where quantum mechanics enters the story in a very strange way. One of the most important principles of quantum mechanics states that two electrons cannot occupy exactly the same quantum state. This creates what physicists call electron degeneracy pressure. The interesting thing is that this isn't pressure in the normal sense like steam pushing a pot lid up. It exists simply because electrons refuse to be squeezed on top of each other. You can think of it as nature putting up an invisible barrier against gravity. And in many cases, that barrier actually works. When a not too massive star dies, electron degeneracy pressure can halt the collapse. What remains is a white dwarf. This is one of the objects that always makes me feel like physics has lost its mind. A white dwarf typically has a mass close to the sun, but a size comparable to Earth, meaning a diameter of about 12,000 kilometers instead of more than 1,300,000 kilometers like our current sun. Try to imagine compressing almost the entire mass of a star into an object 100 times smaller. The material inside is so dense that a teaspoon of it could weigh tons. A person standing on the surface of a white dwarf would feel gravity about 100,000 times stronger than on Earth. The atoms you're familiar with in everyday life almost no longer exist in the normal way. Electrons are squeezed so close together that quantum mechanics becomes the only thing preventing gravity from crushing the entire star further. This is where physics starts to become truly unsettling. Quantum mechanics, which is usually used to describe the tiny world of electrons and atoms, is now controlling the fate of an entire star millions of times larger than Earth. Quantum mechanics and general relativity begin to collide directly inside the corpses of stars. And what I always find fascinating is that all of this isn't happening in a laboratory. It's happening out there in our galaxy right now. The universe is not simple the way 19th century physicists once hoped. Reality at extremely large scales and reality at extremely small scales begin to collide in extremely strange ways. But gravity still isn't done. In fact, the scariest part is that white dwarfs are only nature's first attempt to delay the catastrophe. Because if the star's mass is large enough, even quantum pressure will fail. And when that happens, the universe begins to move toward one of the most terrifying things Einstein's mathematics ever predicted. In 1930, Subramanian Chandrasekhar left India on a ship heading to England to continue his research in astrophysics at Cambridge. What I've always liked about this story is that he didn't own a giant telescope and didn't have a secret laboratory. He only brought paper, a pen, and the equations of quantum mechanics and relativity. During the weeks-long voyage across the sea, Chandrasekhar began calculating what would happen to white dwarfs as their mass increased. And this is when mathematics began leading physics to a very dangerous place. Chandrasekhar realized that electron degeneracy pressure wasn't infinitely strong as everyone had hoped. When matter is compressed strongly enough, the electrons begin moving at extremely high speeds, approaching the speed of light. At that point, you can no longer use classical mechanics. You have to bring Einstein's relativity into the problem. And when Chandrasekhar did that, he discovered a terrifying limit. If a white dwarf exceeds about 1.4 times the mass of the sun, electron degeneracy pressure would no longer be strong enough to resist gravity. Today we call it the Chandrasekhar limit. But in 1930, this result sounded almost like a declaration that nature could allow a star to collapse without limit. Try to think about that from the perspective of physicists at the time. For centuries, physics had operated on the belief that nature must be stable somewhere. Things could shake, explode, or transform, but eventually there had to be some state of equilibrium. Yet Chandrasekhar was saying there were stars that gravity would continue to crush forever. That made a lot of people uncomfortable. And the strongest opponent was Arthur Eddington, one of the most famous astronomers in the world at the time. The same person who had confirmed Einstein was right during the 1919 eclipse. Eddington publicly criticized Chandrasekhar in front of the scientific community. He argued that nature must have some mechanism to prevent infinite collapse. In a way, I can understand how Eddington felt, because if Chandrasekhar was right, it meant the universe could create regions where matter was crushed beyond all normal intuition. But the interesting thing about physics is that mathematics doesn't care what makes humans feel comfortable. Equations have no emotions. They don't negotiate with your intuition. If the equations say gravity wins, then gravity wins. And Chandrasekhar gradually realized that when the mass was large enough, nothing familiar in everyday physics could save the star anymore. Electrons failed, quantum pressure failed, gravity continued to crush the matter inward. This was one of those moments when physics came very close to the modern concept of black holes, even though no one was really using that term widely yet. What I always find fascinating is that this entire catastrophe emerged because you took quantum mechanics and relativity too seriously. If you only used classical physics, you would never see that catastrophe. But when Einstein entered the equation, reality began to become unstable in extremely frightening ways. And what's even stranger is that Chandrasekhar was right. Over time, observations in space began to confirm that there were stars so dense that electron degeneracy pressure couldn't save them. Enormous supernova explosions discovered throughout the galaxy showed that some stars were truly undergoing violent gravitational collapse. The universe apparently had no intention of saving human intuition from the consequences of Einstein's equations. I've always seen this as one of the biggest lessons of science. Reality has no obligation to make sense to human survival instincts. Our brains evolved to throw rocks, hunt, and avoid predators on the African savanna, not to understand objects with densities far beyond anything that exists on Earth. And at this point, nature still seemed to be trying to delay the catastrophe with one final defense mechanism. Because before a star truly turns into what we now call a black hole, the universe still had one last line of defense against gravity. That is the neutron star. If you think white dwarfs are strange enough, trust me, the universe still has many ways to make physics even more uncomfortable. When a sufficiently massive star continues collapsing after a supernova explosion, gravity becomes so strong that electron degeneracy pressure finally fails. Electrons are no longer strong enough to resist the compression, and then something almost unthinkable begins to happen. Protons and electrons are squeezed so tightly that they merge into neutrons through electron capture. Literally, the ordinary structure of matter begins to collapse. The familiar atoms that make up your body, air, water, trees, or this planet almost no longer exist the normal way. The entire star begins to turn into a giant ball of neutrons. And what remains after that catastrophe is a neutron star. I always find it hard to believe that an object with more mass than the sun can be compressed into a sphere only about 20 kilometers wide. You could drive across it in less than half an hour if it wouldn't kill you instantly. Try to imagine that. You take a star more than 1,000,000 times the size of Earth and crush it down to the size of a small city. The density of matter here far exceeds anything we experience in daily life. A teaspoon of neutron star material could weigh billions of tons on Earth. Just a fingertip-sized amount would have enough mass to crush an entire mountain. This is where everyday physics almost completely loses meaning. Familiar concepts like solid, liquid, or gas become useless. Normal atoms no longer exist because electrons have been forced into protons. All matter becomes a terrifying ocean of densely packed neutrons. If you stood near a neutron star, its gravity is so strong that simply falling from a height of a few centimeters would release energy like a bomb explosion. A 70-kilogram person on Earth would feel like they weighed billions of tons on the surface of a neutron star. Light leaving its surface is also heavily redshifted by gravity. Time near it runs measurably slower than farther away in space. You begin to realize that Einstein's relativity doesn't just describe galaxies or the universe on large scales. It is directly affecting the very structure of dead matter. And what I always find fascinating is that this object is still not a black hole. Nature is still fighting back against gravity with a new mechanism. This time, the final line of defense is neutron degeneracy pressure. Neutrons also follow the same quantum rules as electrons. They cannot be completely squeezed on top of each other. Quantum mechanics once again appears to prevent gravity from crushing matter into a singularity. You start to see a very strange pattern in the universe. Gravity keeps trying to force reality to collapse, while quantum mechanics keeps putting up barriers against catastrophe. But those barriers are getting more fragile. And what makes neutron stars even stranger is that many of them spin extremely fast. When the original star collapsed, the law of conservation of angular momentum caused the rotation speed to increase dramatically, like a figure skater pulling their arms in to spin faster. Some neutron stars rotate dozens, hundreds, or even nearly 1,000 times per second. Think about that for a moment. An object heavier than the sun, spinning faster than a circular, saw hundreds of times over. At the same time, they create magnetic fields thousands of billions of times stronger than Earth's and emit extremely powerful beams of radio waves from their two poles. If those beams sweep across Earth, we see extremely precise repeating pulses of signals. In 1967, Jocelyn Bell Burnell discovered such strange radio signals at the Mullard Radio Astronomy Observatory in Cambridge. At first, the signals were so regular that some people in the research group joked that they might be signals from an extraterrestrial civilization. So they temporarily called the first source LGM for little green men. But then physicists realized these were pulsars, extremely fast-spinning neutron stars that theory had predicted years earlier. This is one of my favorite moments in science. An object that once appeared as an almost crazy consequence of equations was finally confirmed by the universe in real life. Reality once again sided with mathematics rather than human intuition. But the scary thing is that even neutron stars are not the final endpoint. Because if the mass is large enough, even neutron degeneracy pressure can fail. Gravity can still win even here. And that's when physics began to move toward one of the most terrifying ideas ever to appear in the history of modern science. What's interesting is that the first person who saw it was Robert Oppenheimer, many years before he became the face associated with the atomic bomb and the Manhattan Project. Most people remember Oppenheimer as the father of the atomic bomb. But before the war, he was an extremely brilliant theoretical physicist, particularly interested in quantum mechanics and astrophysics. In 1939, together with Hartland Snyder, Oppenheimer began studying what really happens when our giant star no longer has any mechanism left to resist gravity. And this is where Einstein's mathematics began to become truly frightening. Up until that point, many physicists still hoped that nature would find some way to prevent the catastrophe from happening. Maybe there would be a new undiscovered pressure. Maybe matter would change state in some way. Maybe the singularity was just a mathematical error. But when Oppenheimer and Snyder followed the relativistic equations all the way to the end, they realized something extremely disturbing. Some stars have no final stable state, no stopping point, no secret last line of defense from nature anymore. If the mass is large enough, gravity will continue to squeeze the matter inward forever. This sounds simple when you say it in words, but try to think about what it really means. An entire star dozens of times more massive than the sun begins to collapse under its own weight. Not exploding, not breaking into pieces, but continuously contracting inward, smaller, smaller, smaller. According to Einstein's equations, the space-time around the star curves more and more strongly as the density increases. And then at some point, there is no longer any path leading outward. The future itself begins to point inward. This is no longer everyday physics. This is where reality begins to behave in a way that almost goes against human intuition. Oppenheimer and Snyder realized that for an observer very far away, the star appears to slow down as it approaches complete collapse. The light from it becomes more strongly redshifted and gradually fades. From the outside, you almost see the star's time freeze. But for the matter falling inward, the collapse continues. This was the first version of the event horizon paradox we talked about at the beginning of the story. And what makes this result so terrifying is that the equations show nothing that can stop the contraction from continuing. If you continue to trust relativity, matter will eventually be compressed into a region of infinite density, a singularity. I think this was one of the most unsettling moments in the entire history of physics, because for the first time, a serious physical theory not only described nature, but also predicted the existence of regions where physics itself might break down. Many scientists at the time simply did not believe nature would actually allow this to happen. Einstein was also uncomfortable with singularities. In fact, many physicists believed that a good theory should not lead to infinities. Because in physics, infinity is often a sign that you have pushed the theory beyond its limits. But the scary thing is that every time people tried to escape the conclusion, mathematics still pulled them back to the same place. Gravity wins, space-time collapses, and a singularity appears at the end of the road. Then history intervened. Just a few months after Oppenheimer and Snyder's work, World War II broke out. Physics suddenly shifted toward radar, uranium, plutonium, and the atomic bomb. Even Oppenheimer himself was drawn into the Manhattan Project at Los Alamos. For many years, research on gravitational collapse was almost forgotten. Black holes at that time were still viewed as mathematical oddities rather than real objects in the universe. But what I've always liked about science is that mathematics doesn't disappear just because humans stop looking at it. Einstein's equations were still there, waiting, quietly, like a machine running in the dark. And when physicists returned to this problem in the 1950s and 1960s, they began to realize that Oppenheimer might have seen something extremely real, something that didn't just exist in the equations, but out in the universe itself. And the strangest thing is that it all led us back to the exact paradox that opened the story. An object can fall into a black hole without ever actually being seen crossing the event horizon. And this is where I think human intuition begins to fail completely. Let's go back to the image of the astronaut falling toward the black hole that we mentioned at the beginning. Suppose he is approaching a supermassive black hole at the center of a galaxy, one with a mass millions of times that of the sun. If you observe from very far away with an extremely powerful telescope, you will see the astronaut's clock running slower and slower as he approaches the event horizon. Each second that passes for him will correspond to many more seconds for you. As he gets even closer, that effect becomes so strong that his motion almost comes to a complete stop. This is not an optical illusion. It is a direct consequence of gravitational time dilation in general relativity. Gravity doesn't just pull on matter, it distorts time itself. A clock near a strong source of gravity always runs slower than one farther away. That has been measured many times with atomic clocks on Earth. But near a black hole, this effect is pushed to the extreme. The light from the astronaut's suit begins to lose energy as it tries to escape the black hole's gravity. Its wavelength is stretched out. The colors gradually shift toward red and then fade. Eventually, the image of the astronaut becomes so faint that it almost disappears completely. From your perspective, he appears frozen right at the event horizon forever. You will never actually see him go inside. But this is the part that makes everything extremely uncomfortable for common sense. For the astronaut himself, nothing special happens at the event horizon. There is no invisible wall. There is no flash of light. There is no cosmic sign that says you have just entered a black hole. His clock is still running normally. His heart is still beating normally. The laws of physics around him are still working as before. If the black hole is large enough, the tidal forces at the event horizon can even be quite weak, meaning he can cross that boundary without feeling anything unusual. This is when you start to realize the real problem. The event horizon is not a physical object in the way we usually think. It is not a hard surface like the ground or a steel wall. It is a boundary in the structure of space-time. Once you cross it, every possible path in the future leads inward. Not because something is pulling you in the usual way, but because the shape of space-time has been bent so severely that going outward becomes impossible, like trying to go further south when you are already at the South Pole. What I always find fascinating is that both of these contradictory descriptions are true at the same time. The distant observer never sees the astronaut cross the event horizon, but the astronaut himself crosses it in his own finite time. Relativity allows two contradictory observations to exist simultaneously without either being wrong. This is something many people find hard to accept when they first learn modern physics. We grow up with the belief that there must be one absolute correct version of reality. But Einstein showed that space and time depend on the observer's state of motion and gravitational field. Reality no longer works like Newton's fixed stage. It becomes something much more flexible. And the more you think about it, the more you realize that black holes are not strange just because gravity is strong. They are strange because they destroy almost all the intuition that humans have built over millions of years of evolution. Our brains were not built to understand places where time can flow differently for different observers. We evolved to throw rocks, run from predators, and find food on a planet with weak gravity and low speeds. But near a black hole, reality begins to behave in a way completely alien to everyday experience. And the interesting thing is that we have only been talking about the outside of the black hole so far. because the truth is that black holes are even stranger than their name suggests. I think the name black hole is one of the best yet most misleading names in the history of science. When hearing it, most people imagine a giant hole opening up somewhere in space, like a cosmic drain sucking everything around it inside. But that is not really what Einstein's equations describe. A black hole is not an open hole in space. It is a region of space-time curved to an extreme degree, and this is when everything starts to become truly hard to imagine. In everyday life, you always think that you can choose which direction to move in the future. You can step left, step right, go up, or turn around. But near a black hole, the structure of space-time is bent so strongly that the directions in the future begin to change. To understand this, physicists often use the concept of light cones. Imagine every second of your existence as a point in space-time. From that point, light can spread out in every direction at the highest possible speed in the universe. If you draw all the paths that light can take in the future, you get a cone-shaped structure called a light cone. In normal space, far from strong sources of gravity, your light cone points fairly straight up toward the future. That means you have many possible paths to move along. But the closer you get to the black hole, the more gravity tilts those light cones inward. At first, the effect is very small, but near the event horizon, that tilt becomes extreme. And inside the event horizon, all light cones are completely tilted toward the center of the black hole. This is the part where human intuition almost completely collapses, because it means going toward the center of the black hole is no longer a choice. It becomes your future in the literal physical sense, just like tomorrow always comes whether you want it to or not. You cannot turn around away from the singularity inside the event horizon any more than you can turn time backward to yesterday. That is why I always say that black holes don't really suck everything in the usual way. The space-time around them is curved so much that every future path leads inward. This is no longer a force in the Newtonian sense. This is the geometry of reality forcing you in a single direction. And then we come to the singularity, which is perhaps the scariest part of the entire story. Most people think a singularity is a tiny ball of matter at the center of the black hole. But Einstein's equations actually say something much stranger. According to the math, the density of matter there becomes infinite, and the curvature of space-time also becomes infinite. In physics, infinite is usually a very bad sign. It often means your theory has reached the limit of what it can meaningfully describe. This makes the singularity one of the strangest things ever to appear in science. It is not a normal object. It is the place where current equations stop working in a physically meaningful way. Einstein never intended to create anything like that. He was just trying to describe gravity more accurately than Newton. But that is what I always find fascinating about science. Sometimes you start with a very simple question, and mathematics leads you to completely unexpected places. Einstein wanted to understand why planets move the way they do. And in the end, his equations led to black holes, time dilation, singularities, and regions in the universe where common sense is almost useless. This is one of the few moments in history where mathematics truly pulled physics far beyond human intuition. And the scary thing is that the deeper they researched, the more physicists realized that black holes might not be the strangest thing Einstein's equations were trying to tell us. Because when they began looking at the entire structure of space-time instead of just a single collapsing star, reality opened up in an even stranger way. One of the people who played the most important role in that was Roger Penrose in the 1960s. I've always thought Penrose had a very rare kind of thinking in physics. He wasn't just interested in how the equations worked, but also tried to see the deep underlying shape of space-time hidden beneath those equations. And what he did completely changed the way physicists visualize black holes. Before Penrose's time, most physicists viewed Einstein's solutions as confusing formulas on paper. But Penrose began finding ways to turn the structure of space-time into something that could be seen through geometry. That was when Penrose diagrams appeared. The interesting thing is that these diagrams don't try to draw space in the usual way, like a geographic map. They compress the entire history of space-time into a finite geometry that humans can observe and think about. It sounds simple, but this was an enormous intellectual leap, because for the first time, physicists could look at the entire life of light, matter, and gravity in a single picture. And then very strange things began to emerge. In classical Newtonian physics, space and time are like a static stage where all events take place. They exist independently of matter. But in relativity, space-time is no longer a stage. It becomes part of the story. It can curve, stretch, twist, and even collapse. Penrose diagrams made this visible in an extremely intuitive way. They show the paths of light, that is, the fastest paths that information can travel in the universe, beginning to be bent by gravity. And when you look at those light paths near a black hole, you realize something very unsettling. Gravity doesn't just bend matter or light. It bends the very causal structure of reality. What can affect what begins to change? Future and past no longer behave according to everyday intuition. This is when the singularity begins to become especially strange. In ordinary thinking, you always imagine the singularity as someplace in space, like a point in the middle of the black hole. But on Penrose diagrams, the singularity sometimes appears more like a moment in the future than a location. That means if you have already crossed the event horizon, going to the singularity becomes almost as inevitable as tomorrow arriving. You no longer move toward the singularity in the usual sense. It lies in your future. This is the part where I think common sense almost completely surrenders to mathematics, because all of our intuition is built on everyday experience where space is fixed and time flows the same for everyone. But in Einstein's world, gravity strong enough can change the very structure of cause and effect. The event horizon at this point no longer resembles a simple physical boundary. It begins to appear as a geometric boundary of reality. Once you cross it, every possible light path points inward, not because of some mysterious pulling force, but because the shape of space-time no longer allows any path leading outward. What I always find fascinating is that Einstein never intended to create ideas like these. He just wanted to fix Newton's gravity. But as physicists continued to dig deeper into those equations, they began to reveal regions of reality that humans had never imagined before the 20th century. Space-time began to behave like a living geometric structure rather than the passive backdrop of the universe. And the deeper they went into the mathematics, the more physicists saw the universe as a giant geometric system where light, time, matter, and causality continuously interact with each other in extremely strange ways. This also made many people begin to realize that black holes might not be the final limit of what relativity allows. Because if gravity is strong enough to bend reality to the point of creating event horizons and singularities, then perhaps Einstein's equations are still trying to tell us something even stranger. And that is when physics began to approach an idea that almost sounds like science fiction. Regions of space-time that can be connected to each other by secret paths through the very structure of the universe. But before getting to that, Einstein's equations produced yet another strange thing. If mathematics allows the existence of a region where everything can only go in but cannot escape, then by the symmetric logic of the equations, the opposite case must also exist. A region where nothing can enter from the outside. That was when the concept of white holes appeared. I've always thought this is one of the ideas that makes people realize how far relativity has gone beyond everyday intuition. A white hole is basically the time-reversed version of a black hole. If a black hole is a place where matter and light can enter but cannot escape, then a white hole is a place where matter and light can only come out, and nothing can enter from the outside. Try to imagine that for a moment. You have a region in space-time that is constantly spitting out matter and light, but every attempt to approach it from the outside fails. According to the equations, the horizon of a white hole works in the opposite way to the event horizon of a black hole. With a black hole, the future of every object points inward. With a white hole, every possible path seems forced outward. This sounds more like a science fiction novel than serious physics. And honestly, when many physicists first saw these solutions, their reaction was almost, "There's no way nature would do something this crazy." But this is the part that makes science fascinating. White holes weren't an idea someone made up for a story. They emerged from valid mathematical solutions of general relativity. If you solve Einstein's equations in certain ways, structures like that appear automatically. This happens quite often in modern physics. You start with a set of equations to describe gravity, and then suddenly mathematics leads you to regions of reality that no one really wants to believe. Of course, many physicists doubt that white holes can actually exist in nature. One of the biggest problems is that they seem extremely unstable. Even a small amount of matter falling in from the outside could destroy their structure. In addition, no one has ever observed anything that is definitely a white hole in the universe. No telescope has seen an object behaving exactly as these solutions predict. And there's another issue that makes many physicists uncomfortable. White holes seem to violate intuition about entropy and the direction of time. In everyday life, every physical system tends to go from order to greater disorder. But white holes look like a process running the movie of reality backward. That makes them even more suspicious in the eyes of many scientists. But what I've always found important here is not whether white holes are real or not. What's important is that mathematics led us to that idea naturally. Physics has repeatedly forced humans to consider possibilities that sounded completely absurd at first. Remember that there was a time when people also thought black holes were just oddities of the equations. Even Einstein doubted them. But then the universe gradually showed that the equations could be right in ways that everyday intuition simply couldn't accept. And the deeper they researched, the more physicists realized that black holes and white holes are not two completely separate ideas. In some extended solutions of relativity, they began to connect with each other in extremely strange ways, as if space-time was folding itself into secret bridges through the very structure of the universe. And what always fascinates me is that this idea didn't first appear in science fiction. It emerged from Albert Einstein and Nathan Rosen themselves in 1935. At the time, the two were trying to study the solutions of general relativity more deeply and understand what really lay behind the strange singularities in the equations. Instead of viewing black holes simply as the endpoint of matter, they began to realize that the equations also allowed a much stranger structure. If space-time could curve, stretch, and collapse, then mathematically it could also fold in a way that connected two very distant regions with a bridge. Today we call that structure an Einstein-Rosen bridge. This sounds almost impossible when you think about it with everyday intuition. In daily experience, if you want to go from one point to another, you have to travel the entire distance in between. But relativity began to suggest that distances in the universe don't necessarily work that way. Imagine you draw 2 points very far apart on a flat sheet of paper. If you move on the surface of the paper, you have to cover the entire distance between those 2 points. But if you fold the paper so the 2 points touch, the distance almost disappears. That's the kind of idea that the geometry of space-time and relativity began to allow. According to Einstein's equations, two extremely distant regions of the universe could be connected directly by a path through the curved structure of space-time. The interesting thing is that the entire idea came from mathematics rather than cinematic imagination. Einstein never tried to create cosmic gateways or shortcuts across the galaxy. He was just trying to understand gravity. But his equations kept leading physics to places stranger than anything humans had imagined before. Later, people began calling these structures wormholes. The basic idea is that instead of traveling through ordinary space between 2 points, you could go through a geometric tunnel that connects them directly. In theory, this means two regions separated by millions of light years could be linked by a very short distance in the true structure of space-time. This was one of those moments when reality began to behave even stranger than almost any ancient myth ever created. And of course, As soon as physicists started thinking about this, their imagination immediately went far beyond just one galaxy. Some began to speculate that if wormholes really existed, they might not only connect two different places in the same universe. Perhaps they could connect two completely different universes. Just saying that out loud was enough to make physics sound like fantasy. But that's what I've always loved about science. The universe has no obligation to fit human feelings of what's reasonable. If mathematics leads to that conclusion, physicists are forced to at least consider it seriously. And what's even more unsettling is that the equations seem to have no objection to this possibility. When you view space-time as a dynamic geometric structure rather than static emptiness, such bridges begin to become natural consequences of extreme curvature. This is where physics came very close to the boundary where intuition almost completely collapses. Our brains evolved on a small planet at low speeds with weak gravity. We were not built to imagine a universe where space can fold in on itself like a sheet of paper. But Einstein's equations seem to be saying that reality is far deeper than everyday experience. And the interesting thing is that the deeper you go into these equations, the more the universe resembles a living structure that can be bent, connected, and distorted in almost unimaginable ways. However, just like many other strange ideas in relativity, the biggest problem wasn't, does mathematics allow it? The problem was whether nature would actually allow it to exist stably, because the more carefully they studied it, the more physicists began to suspect that such tunnels would be extremely fragile. Even a small fluctuation of matter or energy could cause the entire structure to collapse almost instantly. And that was when physics once again became ruthless, with ideas that sounded too beautiful to be true. Because as soon as physicists began to seriously study wormholes, they quickly discovered a huge problem. Gravity seemed to hate their existence. According to relativity's equations, the structure of the wormhole itself tends to collapse almost immediately. Imagine you try to create a tunnel through a mountain using extremely soft material. The weight of the mountain itself would cause that tunnel to collapse before anyone could pass through. Something similar seems to happen with space-time. Gravity keeps trying to squeeze the throat of the wormhole shut. And what makes everything worse is that any object trying to pass through it could cause the structure to become completely unstable. Just the energy and mass of the spaceship or astronaut entering would be enough to distort the space-time around the wormhole even more, causing it to collapse before the journey is complete. This was the moment when the universe seemed to be saying, there are no easy shortcuts. But then mathematics continued to produce even more strange ideas. Some solutions showed that it might be possible to keep the wormhole open if there existed a very special form of matter or energy called negative energy. This is the part where physics begins to sound almost completely insane. In everyday life, we always think of energy as positive. A flying ball has positive energy. Light has positive energy. A shining star has positive energy. But in some special quantum configurations, equations allow regions where energy density becomes negative relative to the surrounding environment. This idea isn't random imagination. It actually appears in some quantum effects like the Casimir effect, where two metal plates placed very close together create a small change in vacuum energy. Some physicists began to wonder whether this strange energy could be used to counteract the collapsing tendency of wormholes. Because if gravity always pulls spacetime closed, perhaps negative energy could act as a geometric push to keep the throat of the hole open. But this is when reality becomes uncomfortable in the true style of modern physics. There is no clear evidence that stable matter with negative energy exists on a large scale in nature. The quantum effects we observe are extremely small and exist for very short times. No one knows whether they can be accumulated in sufficient quantities to keep an entire cosmic structure open. And then quantum mechanics made everything even more complicated. One of the strangest things about quantum mechanics is that the vacuum is not truly empty. When I was young, I used to think the space between the stars was basically nothing. But quantum field theory shows that what we call vacuum is actually full of continuous energy fluctuations. Virtual particles appear and disappear constantly. Space-time at extremely small scales looks more like a chaotic ocean than a quiet void. That means a wormhole, which is already extremely fragile, would also have to exist amid this continuously fluctuating quantum storm. And this is the part that makes many physicists pessimistic about the possibility of stable wormholes. Quantum effects could be amplified extremely strongly near such extreme geometric structures. A small fluctuation in the vacuum could be enough to make the wormhole's throat collapse at the speed of light. In other words, even if relativity allows wormholes to exist, quantum mechanics could immediately destroy them before any information could pass through. This is the kind of thing that happens constantly in modern physics. You find a mathematically beautiful idea, and then the universe coldly finds a way to prevent it from working in real life. And I think this is one of the most interesting things about science. Physics doesn't care what sounds poetic or convenient for humans. It only cares about how reality actually works. Sometimes equations open astonishing doors, and then other equations immediately slam them shut. But even if wormholes may not exist stably, this entire journey still reveals something extremely important. Einstein's relativity turned space-time from a stage into a dynamic structure that can curve, twist, collapse, and even connect distant regions of the universe. And the scary thing is that we still haven't reached the strangest part of the story. Because when physicists began to study spinning black holes instead of stationary ones, Einstein's equations opened up an entirely new level of strangeness. The interesting thing is that almost everything in the universe spins. Earth spins, the sun spins, galaxies spin, the giant gas clouds that create stars also spin. So it would be strange if black holes, which are born from the collapse of spinning stars, were completely stationary. For many years, physicists mainly studied Schwarzschild black holes, that is, the ideal non-rotating and perfectly symmetric type. But in 1963, a New Zealand mathematician named Roy Kerr found a new solution to Einstein's equations describing rotating black holes. And honestly, what he discovered made ordinary black holes look almost simple. A Kerr black hole doesn't just curve space around it. It drags and twists space-time itself according to its rotation. This is where relativity begins to become almost impossible to imagine with everyday intuition. In Newtonian physics, space is like a static stage that objects move through. But in relativity, if an object is heavy enough and spins extremely fast, it can drag the entire surrounding space-time structure with it. This phenomenon is now called frame dragging. Imagine you place a bowling ball on a rubber sheet and spin it extremely fast. The sheet doesn't just dent downward, but also twists around the ball. That's the closest image we can use to visualize what happens near a rotating black hole. But reality is actually much stranger than that example, because what is being twisted here is not just space, but also time. Near a rotating black hole, space itself begins to move. This sounds almost meaningless the first time you hear it. We are used to thinking objects move through space, but near a Kerr black hole, space itself is being swirled around the black hole like water around a giant drain. And the closer you get, the stronger this twisting becomes. Eventually you enter a region called the ergosphere. This is one of the strangest things Einstein's equations ever predicted. In the ergosphere, no object can stand still anymore. Not because of some wind or pushing force, but because space-time itself is being dragged too strongly. No matter how hard you try to stay in place, reality around you still pulls you to rotate with the black hole. You begin to realize that familiar concepts like standing still or motion no longer have simple meanings. What always fascinates me is that all of this didn't come from anyone's wild imagination. It emerged directly from Einstein's equations. And the more they studied the Kerr solution, the stranger physicists found it compared to the original Schwarzschild black hole. In a non-rotating black hole, the singularity is described as an infinite point at the center. But in a rotating black hole, the singularity is no longer a point. It becomes a ring. This may sound like just a small mathematical detail, but its consequences are extremely significant, because when the singularity becomes a ring instead of a point, the structure of space-time inside begins to change in an almost unimaginable way. Some solutions suggest that orbits may exist that pass through the region inside the ring singularity instead of hitting the singularity directly. This is when physics truly began to approach the border of science fiction. According to some mathematical extensions of the Kerr solution, matter passing through that region might not be crushed immediately, but instead proceed into other regions of space-time. I remember the first time I read about this, the feeling was almost like the universe was trying to say that reality is far deeper than what common sense had ever allowed us to imagine. And the scary thing is that the equations didn't seem to completely rule out that possibility. Of course, this doesn't mean you can fly a spaceship through a black hole, like in movies. There are countless unsolved physical problems. Quantum effects, radiation, gravitational waves, and instabilities could destroy the entire structure before anything could pass through. But the important thing isn't whether humans could do it or not. The important thing is that mathematics opened the door for that possibility to exist. And this is where physics becomes both beautiful and terrifying. You start with Newton's gravity to explain an apple falling from a tree. Then a few generations later, the equations evolve into something that can predict regions in the universe, where space twists, time curves, and singularities can act like gateways to other parts of reality. This is when the Kerr solution began to become truly frightening for human intuition. In an ordinary Schwarzschild black hole, the singularity is described as an infinite density point at the center. But in a rotating black hole, the singularity is no longer a point. It becomes a ring. This may initially sound like a small geometric change, but it actually alters the entire internal structure of the black hole. Try to imagine the difference between a completely closed wall and a ring with a gap in the middle. Some mathematical solutions of relativity began to show that objects could pass through the region inside the ring singularity without colliding directly with the singularity itself. This is the part where physics starts to sound almost insane. According to the equations, the space-time inside a rotating black hole is not simply go in and in. Its structure is far more complex than what physicists initially imagined. The paths of light, the causal cones, and the entire geometry of reality inside it begin to fold and reconnect in ways that are almost impossible to visualize with common sense. Some mathematical orbits seem to allow matter to pass through the region inside the ring singularity and then emerge somewhere else in space-time. When I first read about these solutions, the feeling was almost like the equations were trying to completely destroy ordinary human intuition. You start with Newton's gravity to explain planetary motion, and you end up with structures where reality can fold itself into paths leading to other regions of the universe. And what made many physicists feel both fascinated and uncomfortable was that mathematics truly allowed this to appear on paper. Some extended solutions even suggested that these paths could connect to completely different regions of space-time, almost like a different universe in the geometric sense. I know this sounds like something you would see in a novel rather than a serious physics paper, but this is exactly what makes relativity one of the most disturbing theories ever created. It continuously leads humans to conclusions that everyday instincts simply cannot accept. However, reality once again began to push back, because the deeper they researched, the more physicists realized that this entire structure could be extremely fragile. Even an extremely small quantum fluctuation could completely destroy the geometry inside a rotating black hole. Remember that the quantum vacuum is not truly quiet. Space at extremely small scales is full of continuous energy fluctuations that appear and disappear. And near regions of extreme gravity, like the singularity, those fluctuations can be violently amplified. This made many physicists suspect that the passing through the singularity orbits might only exist in ideal mathematics and never be stable in the real universe. Just a very small amount of matter or radiation falling in at the right moment could cause the entire internal structure to collapse into gravitational chaos. This is one of the recurring problems in modern physics. Mathematics often opens astonishing doors, but reality does not always allow humans to step through them. And honestly, until the late 1980s, no one knew for sure whether solutions like these had real physical meaning. They might reflect something very deep about the structure of space-time. But they could also be a sign that Einstein's relativity was being pushed beyond the limit where it still worked accurately. This happens quite often in physics. A theory can be extremely correct within a certain range, and then begin to produce infinities and paradoxes when pushed too far. Singularities may be exactly the signal that we are still missing an important part of reality. But what I always find fascinating is that whether right or wrong in the end physically, Einstein's equations continuously forced humans to think about the universe in ways that no one before the 20th century had ever imagined. They turned space-time into something that can curve, twist, collapse, reconnect, and perhaps even open paths through the very structure of reality. And at this point in the story, you begin to wonder about something quite unsettling. Is the universe really built in the way human intuition has always trusted? Or is reality far deeper than all the experiences our brains have evolved to understand? I think this is the scariest part of the entire story. Not black holes, not singularities, not the tunnels through space-time. The scariest thing is that the equations keep being right. That's what makes me feel slightly uneasy multiple times when thinking about modern physics. Because if you look back at the history of science, the strange thing keeps happening in the same way. A physicist writes a few equations to explain something relatively simple. Then mathematics begins to lead them to conclusions that sound completely absurd. At first, everyone objects. They say it can't be right because it goes against common sense. But then experiments or observations appear, and the universe once again sides with mathematics. That happened with relativity. It happened with black holes. And it continues to happen in modern physics. I think the deep reason is because the human brain was never built to understand reality at this level. We evolved on the African savanna to recognize predators, find food, throw rocks, and avoid falling off cliffs. Our instincts work well in a world of low speeds, weak gravity, and medium sizes. But the real universe does not operate under those conditions. Light travels at nearly 300,000 kilometers per second. Neutron stars have densities beyond imagination. Black holes make time flow differently for different observers. There is no reason why human evolutionary brains should feel natural with such things. And this is what relativity continuously forces us to accept. Common sense is not a law of physics. It is only a mental habit formed from everyday experience on a small planet. Einstein repeatedly destroyed that intuition with mathematics. In the everyday world, time always flows the same for everyone. But relativity shows that is wrong. In daily life, you think heavier objects are harder to move, but space itself stays still. But near a rotating black hole, space-time itself begins to be dragged and twisted with the motion. In ordinary life, you always think there exists an absolute present for the entire universe. But relativity shows simultaneity depends on the observer. Every step forward in modern physics makes reality stranger rather than simpler. What I always find beautiful about science is that it succeeds precisely because mathematics is stronger than instinct. If physicists only believed in everyday intuition, we would never have relativity, quantum mechanics, or atomic physics. Those theories exist because humans accepted following the equations even when instinct screamed that it was absurd. And history has repeatedly shown that was the right decision. I think this is one of the most profound lessons of all modern science. Reality has no obligation to make sense to human emotions. The universe was not designed to be convenient for our intuition. We are just an intelligent primate species, smart enough to begin seeing the true structure of reality, but not yet smart enough to feel comfortable with it. The deeper you go into physics, the more you begin to feel that the universe is fundamentally alien to ordinary human experience. Space-time can curve, time can stretch. The quantum vacuum is not truly empty. Singularities can exist in the equations. And the most unsettling thing is that mathematics has repeatedly predicted these things before humans observed them in the universe. Einstein's equations opened up a universe stranger than almost any 19th century imagination. Before relativity, many physicists believed the universe was basically a giant machine operating on Newton's absolute stage of space and time. But then Einstein turned space and time into something flexible, dynamic, and deformable by matter. That alone was enough to make reality far stranger than what our ancestors imagined when looking at the night sky. But the interesting thing is that even relativity may not be the deepest layer of reality, because every time physics begins to think it understands the universe, quantum mechanics appears and makes everything even more confusing. This is where the story of black holes truly begins to become dangerous for the entire foundation of modern physics. Throughout the 20th century, there were two theories that completely changed the way humans understand reality. One was Einstein's relativity, describing gravity, space-time, and the universe on large scales. The other was quantum mechanics, describing the world of atoms, electrons, and extremely small particles. And what's fascinating is that both are correct in an astonishing way. Relativity helps predict planetary orbits, time dilation, and the operation of satellites. Quantum mechanics created the transistor, the laser, and nearly all modern technology. But the problem is that the two most successful theories in physics are not completely compatible with each other. In most situations in the universe, you can use relativity or quantum mechanics separately without major problems. But near black holes, especially around the singularity, both extreme gravity and quantum effects become important at the same time. And that is where everything begins to fall apart, theoretically. One of the first people who truly pushed physics into this dangerous territory was Stephen Hawking in the early 1970s. What I've always found fascinating about Hawking is that he dared to apply quantum mechanics to the very thing many physicists viewed as the absolute abyss of the universe. Up until then, black holes were seen as objects that only sucked everything in and never gave anything back. Once light crossed the event horizon, it disappeared forever. But Hawking began to think about what happens with the quantum vacuum around the event horizon. And this is when reality became stranger once again. According to quantum field theory, the vacuum is not truly empty. Space is full of quantum fluctuations, where pairs of particles and antiparticles continuously appear and disappear in extremely short times. Normally, they annihilate each other almost immediately. But Hawking realized that near the event horizon, the black hole's extreme gravity could separate these particle pairs before they could annihilate. One particle falls into the black hole while the other escapes outward. To a distant observer, the process looks as if the black hole is emitting radiation. This was extremely shocking for physics at the time, because it meant black holes were not completely black. They actually glow very faintly due to quantum effects. Today we call it Hawking radiation. What makes this result disturbing is that the energy of the escaping particle has to come from somewhere. According to Hawking's calculations, the black hole gradually loses mass to produce this radiation. In other words, black holes can evaporate over time. For stellar mass black holes, that process is extremely slow, far longer than the current age of the universe. But in principle, if you wait long enough, the black hole could eventually disappear completely. This is when physics began to fall into a truly dangerous paradox. Remember that in quantum mechanics, information about the state of a physical system is not allowed to disappear completely. That is an extremely deep principle of the theory. But if matter falls into a black hole and the black hole evaporates into random thermal radiation, what happens to all the information of the original matter? Is it destroyed? If the answer is yes, quantum mechanics may be wrong somewhere. If the answer is no, relativity may be missing something extremely important. This is what is now called the black hole information paradox. And honestly, it is one of the clearest signs that modern physics is still incomplete. What's fascinating is that thermodynamics, the theory of heat and entropy, began to appear right at the place once viewed as the absolute abyss of the universe. Black holes now not only have gravity, they have temperature, they have entropy, they can emit radiation and lose energy. An object once seen as an infinite dark pit has now become a real thermodynamic physical system. And every new step makes reality more confusing rather than simpler. This made many physicists begin to feel that black holes are not just strange astronomical objects. They may be where the universe is trying to reveal the limits of all current physics. Because when relativity and quantum mechanics meet near the event horizon, the foundations of science begin to collide directly with each other in a way that no one yet knows how to fully resolve. This is when physics entered a real crisis. One of the deepest principles of quantum mechanics states that information cannot be completely destroyed. This may sound a bit abstract at first, but it is extremely important. In quantum mechanics, if you know the exact state of a system at one moment, the equations allow you, in principle, to calculate its state at any other moment. Information can be dispersed, transformed, or become extremely difficult to recover, but it is not allowed to disappear from the universe. This is one of the mathematical foundations of the entire theory. But then black holes appeared and began to ruin everything. Imagine you throw a book into a black hole. The book contains information, the atomic structure of the paper, the positions of the electrons, every printed word on the page. According to classical relativity, all that information crosses the event horizon and disappears from the rest of the universe. If the black hole existed forever, the problem might not be too serious. The information would still be somewhere inside. But Hawking showed that black holes can evaporate over time through thermal radiation. And this is where the real paradox appears. If the black hole eventually disappears completely, what happens to the information in the book? Is it destroyed? If the answer is yes, quantum mechanics has a serious problem. If the answer is no, then relativity, or the way we understand black holes, must be missing something extremely fundamental. This is not a philosophical question like, if a tree falls in the forest and no one hears it. This is a real mathematical conflict between the two most successful theories in modern physics. And the unsettling thing is that both theories are extremely accurate in their own domains. Relativity correctly predicts time dilation, planetary orbits, and gravitational waves. Quantum mechanics accurately predicts atomic behavior to dozens of decimal places. But near black holes, they begin to contradict each other directly. This was the moment when many physicists began to realize that current physics may not be complete. For most of the history of science, people always hoped that the more we understood the universe, the simpler and clearer reality would become. But black holes seem to be saying the opposite. The deeper you go into the structure of space-time, the more the foundations of physics begin to crack. Singularities are especially frightening in that sense. According to Einstein's equations, the density of matter at the singularity becomes infinite, and the curvature of space-time also becomes infinite. But infinities in physics are often a signal that the theory has gone beyond the limit where it can still function. They are like error messages from the universe. Many physicists believe that singularities are not real objects in the ordinary sense, but places where familiar laws completely break down. Relativity is no longer sufficient. Quantum mechanics alone is also not enough. We need a deeper theory that can connect gravity with the quantum world into a unified framework. This is why so many physicists in the 20th century began searching for what is called quantum gravity. Some studied string theory. Some studied loop quantum gravity. Some tried to quantize space-time directly. But until before 1988, no one had truly resolved the black hole information paradox. The universe seemed to still be keeping its biggest secret right at the place where gravity is strongest. What's fascinating is that the more they tried to solve this paradox, the more physics discovered new questions. Is information really encoded on the event horizon? Is space-time only an emergent phenomenon from a deeper quantum structure? Does reality at the fundamental level work completely differently from all human intuitions? This is where science becomes both frustrating and beautiful to me. We often think science is a journey from mystery to certainty, but many times science progresses by discovering things it doesn't yet understand. Each paradox is like a small crack in the wall of reality, where the universe reveals that current models are still incomplete. And the funny thing is that doesn't make science weaker. It makes science more alive, because uncertainty is exactly the engine that keeps physics moving forward. If everything were completely clear, there would be no reason left to keep asking questions about the universe. And I think that's one of the most beautiful things about modern physics. It continuously proves that reality does not operate according to human intuition. In fact, if you look back at the history of science in the 20th century, nearly every major breakthrough began with something that sounded absurd to everyday intuition. When Einstein published relativity in the early 1900s, many people viewed it as strange mathematics rather than a true description of nature. The idea that time could flow differently for different observers sounded completely ridiculous to most physicists at the time. The notion that space could curve because of matter sounded more like philosophy than physics. But then observations began to appear. Light really was bent near the sun. Clocks really did run slower in stronger gravity. And the universe gradually confirmed that Einstein was right, no matter how strongly common sense objected. The same thing happened with black holes. For many decades, many physicists viewed them as impossible objects that only existed on paper. Even Einstein was uncomfortable with the idea that a star could collapse into a singularity. But then evidence began to accumulate. Pulsars were discovered. Binary star systems showed the presence of extremely heavy invisible objects. Galactic centers revealed enormous sources of gravity that couldn't be explained by normal stars. Little by little, the universe once again sided with mathematics rather than human intuition. I think this is the hardest part of science to accept. It advances not by protecting our sense of comfort, but by forcing us to accept uncomfortable conclusions if the evidence and equations lead there. Humans always want reality to be simple, stable, and easy to understand. But modern physics continuously shows that the universe is far stranger than what common sense ever promised. What's fascinating is that mathematics often sees reality before telescopes and experiments do. Black holes appeared in the equations decades before there was strong observational evidence. Gravitational waves were predicted by Einstein in 1916, but humans only directly measured them in 2015. The positron appeared in Dirac's equation before it was discovered in nature. This is a repeating pattern in physics. Equations seem to see parts of the universe that human intuition is completely blind to. Einstein never tried to create black holes. He didn't try to create wormholes or singularities. He was just trying to describe gravity more accurately than Newton. But when he followed the mathematics all the way, his equations began to open up regions of reality far beyond the imagination of that era. I think this is what makes science completely different from myth or philosophy. Science allows reality to contradict human expectations. If the equations and observations point to something strange, physicists are forced to confront it whether they like it or not. And the most beautiful thing about this entire journey is that reality is always bigger than imagination. Every time humans think they're about to fully understand the universe, nature opens up another layer that's even stranger. Newton thought gravity was an invisible force between objects. Einstein turned gravity into the geometry of space-time. Quantum mechanics showed that the vacuum is not truly empty. Black holes led to the information paradox. Singularity suggests that current physics is still incomplete. The deeper you dig, the more reality looks like something that goes beyond every simple story humans have ever told themselves. Honestly, the more I understand physics, the less I feel the universe is easy to understand. When we were kids, Many people thought science would gradually turn every mystery into simple formulas. But the experience of modern physics is almost the opposite. Every big answer opens up many deeper questions. We understand how stars produce energy, then we discover black holes. We understand relativity, then we discover the information paradox. We understand quantum mechanics, then we realize it doesn't fully mesh with gravity. The universe doesn't become smaller as science progresses. It becomes bigger, stranger, more beautiful. And that is the central point of this entire story. The strangest things in physics don't appear because scientists tried to imagine something weird. They appear when humans take Einstein's mathematics too seriously. I think this is the most important thing to remember from this whole story. Einstein never sat down and said, I'm going to create black holes, singularities, or tunnels through space-time. He just tried to describe gravity more accurately than Newton. That's all. He wanted to understand why Mercury moved slightly differently from old predictions. He wanted to understand how light responded to gravity. He wanted to build a more consistent theory of space and time. But then the equations began leading to places no one expected. Black holes appeared. Time dilation appeared. Curved space-time appeared. Event horizons appeared. Wormholes appeared. And what's fascinating is that all of those things came from the same set of equations. This is the part that always makes me feel science is both beautiful and unsettling, because it shows that reality is not built according to what humans want to be true. The universe operates according to a mathematical structure far deeper than our instincts. In everyday life, intuition works pretty well. If you throw a ball, it falls down. If you push a heavy object, it's harder to move. But that intuition is only refined for the very small environment of Earth. When you go to speeds near light, extreme gravity, or cosmic scales, instinct becomes almost useless. And that's why mathematics becomes more important than common sense in modern physics. I've always thought one of the most uncomfortable lessons of science is that mathematics is often more honest than human feelings. If Einstein had only trusted everyday intuition, he would never have accepted that time could stretch or space could curve. If physicists had only trusted instinct, they would have rejected black holes as nonsense. But the universe has repeatedly sided with the equations. That has happened so many times it can't be considered coincidence. Modern physics continuously forces us to accept that reality is not like daily life. In the world of relativity, there is no absolute time for everyone. Two people moving differently, may disagree about the time interval between events. Gravity can make clocks run slower. Space can be twisted by rotating objects. A star can collapse into a region where light cannot escape. These things sound absurd if you judge them by ordinary intuition. But they emerge naturally from mathematics. And that is what made relativity the greatest intellectual revolution of the 20th century. It completely changed the way humans understand space and time. Before Einstein, many physicists thought space was a static stage, and time was a cosmic clock running evenly for everything. After relativity, space and time became a dynamic structure that can curve, stretch, twist, and respond to matter. Reality became far more flexible than anything the 19th century had imagined. What's unsettling is that strange things don't appear because the universe wants to be strange. They appear because the universe was not built to fit human instinct. Our brains did not evolve to understand four-dimensional space-time or quantum vacuum. We just happen to be smart enough to begin seeing them through mathematics. And the deeper you go into theoretical physics, the more you feel like you're moving far away from normal human experience. I think theoretical physics is really a journey following mathematics to the place where imagination collapses. You start with a simple equation describing gravity. Then step by step, the equations lead you to time dilation, black holes, singularities, the information paradox, and structures where reality itself behaves in ways that are almost impossible to visualize. Many times it feels like mathematics is pulling humans to peek into the deeper foundation of the universe, something evolution never prepared our brains to face. But the most beautiful thing about this entire journey is that mystery does not disappear as science progresses. It only becomes deeper. Every major discovery does not close the final door of reality. It opens even more new doors that are stranger still. And perhaps that is the most amazing thing about the universe. The more we understand it, the more we realize we have only just begun to see the true structure of reality. And perhaps that is the most appropriate place to return to the image that opened this entire story. An astronaut falling toward a black hole in the almost absolute darkness of the universe. From very far away, you see him slowing down near the event horizon. The light from his suit gradually turns red and then fades as if time is freezing around him. But for the person falling himself, the clock is still running normally. His heart is still beating normally. He just continues moving into a region of extremely curved space-time, where every future path leads inward. I think the entire strangeness of modern physics lies in that very paradox. The universe does not care at all what makes humans feel reasonable or comfortable. Nature has no obligation to fit human intuition. We are only used to thinking reality should resemble daily experience because our brains evolved in a very small and limited environment. But when you look deeper into the universe, you begin to realize reality is vastly larger and stranger than anything common sense ever prepared us for. Einstein only wanted to understand gravity, but his equations ultimately revealed a universe where time can slow down, space can curve, light can be bent, stars can collapse into singularities, and perhaps reality even contains structures that human imagination cannot keep up with. I think if you told a 19th century physicist that equations about gravity would one day lead to black holes, time dilation, wormholes, and quantum information paradoxes, they would think you were telling mythology rather than science. But that is precisely what is most beautiful about physics. Reality is always bigger than our imagination. Every generation of physicists thinks they are getting close to the complete picture of the universe. Then, mathematics opens another new door, leading to even stranger questions. Newton thought he had explained gravity. Einstein showed that gravity is actually the geometry of space-time. Hawking showed that black holes have temperature and can evaporate. Quantum mechanics continues to destroy the idea of absolute certainty. It's as if every time science climbs one mountain, we see even more mountain ranges in the distance. And honestly, I don't think that's a weakness of science. It's a sign that science is still alive. Many people think the goal of physics is to remove mystery from the universe. But the real experience of science is almost the opposite. Every big answer makes reality deeper and stranger. We don't end up with less mystery. No, we end up with more sophisticated mysteries. When humans were children, we looked at thunder and lightning and thought it was the anger of the gods. Now we understand electromagnetism, plasma, and the atmosphere. But instead of the universe becoming smaller, science has led us to neutron stars, black holes, quantum vacuum, and paradoxes where space-time itself begins to destabilize. Mystery doesn't disappear. It evolves. I think that's why physics is so beautiful. It forces humans to confront reality instead of comfort. It doesn't allow us to keep simple stories just because they are more comfortable. If the equations and observations say the universe is stranger than imagination, science must follow that truth, no matter how unsettling it is. And what always fascinates me is that every major step forward in physics begins with someone brave enough to trust mathematics more than their own instincts. Einstein did that with relativity. Dirac did that with antimatter. Hawking did that with black holes. They didn't invent reality. They were just bold enough to follow the equations to where intuition collapses. Perhaps the most astonishing thing is that black holes may not even be the strangest part of the universe. They may just be the beginning. If 20th century physics led us from classical gravity to curved space-time, singularities, and information paradoxes, who knows what the next century will open up? There may be deeper structures beneath quantum mechanics. Space-time may only be an emergent phenomenon from something even more fundamental. The entire way humans currently think about reality may one day be seen as primitive in the same way we view physics before Einstein. That doesn't make science weaker. It makes science alive, because the universe still has the ability to surprise us. And I think that is the best part of this entire story, not how much we have understood, but how much there still is that we don't understand. I've always felt that if one day physics becomes completely predictable and has no more mysteries, that would be the saddest day for science. But the universe doesn't seem to intend for that to happen. The deeper we look into reality, the more layers we see beneath. The more we learn, the more we realize how little we know. And honestly, I don't find that depressing at all. I find it wonderful. Because the most interesting thing in the universe is probably the fact that there is still so much that humanity hasn't understood. If you like stories where science is stranger than imagination, please subscribe to the channel to continue exploring the deepest mysteries of the universe with me. And in the next video, we will take another step into reality, where every new equation can completely change the way you look at the world around you.